In this session, we will be discussing about limiting molar conductivity. What do you mean by limiting molar conductivity? The graph which you are seeing here, you have observed this graph even in your session, the previous session, the same graph of your molar conductivity, that is molar conductance versus your root C. The same graph, and the same electrolyte I have taken, a strong electrolyte, that is your KCl. It's a strong electrolyte. So the same graph, we know the graph is a straight line wherein there is no much of slope. The same graph I have taken here. So if this graph, for this graph, that is the KCl strong electrolyte graph, if I extrapolate this graph like this, and if I join it to your y-axis like this, that is, you are diluting the solution more and more, that is KCl, the dilution starts here, you are diluting more and more such that the concentration is 0. You can observe here the concentration is 0, and this point wherein the graph, that is this line, extrapolated line of your graph which touches your y-axis wherein concentration is 0, the molar conductivity of this electrolyte at this point is maximum, that is diluting this KCl solution more than this, over this will not any increase, that it will not increase its molar conductivity. That is, this is the last point of the increase in molar conductivity of this electrolyte. That is, it is the maximum molar conductivity of this KCl wherein the concentration is 0. So this is the maximum molar conductance of the electrolyte. So this point, the intersection point on y-axis, upon extrapolating your graph, this point where concentration is 0, remember here concentration is 0, and the molar conductivity of the electrolyte is maximum. This point wherein the maximum molar conductivity of a strong electrolyte is observed, where concentration is 0, whereas dilution is, since concentration is 0, here you can observe that dilution is at its maximum, that is dilution is infinite. So this point wherein the concentration is 0, which means dilution is infinite, the molar conductivity is at its maximum molar conductivity is called as your limiting molar conductivity. Limiting molar conductivity. Limiting molar conductivity. So what do you mean by limiting molar conductivity? Very simple. It is the maximum molar conductance of an electrolyte where concentration is 0 and at infinite dilution is called as your limiting molar conductivity. It is represented by lambda m, it's your molar conductivity at infinite dilution, so it is represented as naught. Or even in some textbook you can observe it is also represented by lambda m infinity, which means that it is the molar conductivity of an electrolyte at infinite dilution. So molar conductivity, that is limiting molar conductivity, I can define it as, it is the maximum molar conductance of an electrolyte at concentration is equal to 0 or at infinite dilution. So it's the maximum molar conductance of an electrolyte at concentration is equal to 0. You can observe C is 0 here, and at infinite dilution, concentration 0 means dilution is infinite. So that point of molar conductance of an electrolyte is called as your limiting molar conductivity. It is symbolized by lambda m naught and lambda m infinity. So both the representations are correct. The same graph, the same plot, if I look it for your weak electrolyte, as in your previous session also, if I take the same plot of lambda m, that's your molar conductivity versus root C for a weak electrolyte, it looks like this. That is, I am taking a plot of your acetic acid, CH3, COOH, acetic acid. The plot looks like this. You have already seen in your previous session too. Upon increasing the dilution, the graph goes like this. So, however you increase the dilution, that is up to 0 or infinite dilution, you cannot calculate your molar conductivity at infinite dilution from this method. So, as a result, in order to calculate the limiting molar conductivity for a weak electrolyte is made through your Kohlrausch's law. That is, the acetic acid, which is a weak electrolyte, upon dilution, this graphical method you can observe the graph goes like this, which never meets your y-axis, wherein you cannot identify, you cannot calculate the limiting molar conductivity of weak electrolyte by this method. As a result, one of the application of your Kohlrausch's law is your determining the limiting molar conductivity of your acetic acid from your strong electrolytes, that is from your weak electrolytes. For your weak electrolytes, it is from your strong electrolytes. So that's one of the important thing wherein you are calculating the limiting molar conductivity of weak electrolytes, which cannot be done through this graphical method. So as a result, now we have to see about what is Kohlrausch's law, what does it tell about this limiting molar conductivity of weak electrolytes, and it is one of the very important laws that has to be studied for your board exams. So from this method, lambda m naught of weak electrolytes cannot be calculated. So as a result, you are using a new law which helps in determining this limiting molar conductivity of acetic acid weak electrolytes, and that is your Kohlrausch's law. Kohlrausch's law. Let us see what is this Kohlrausch's law is. So before going to a Kohlrausch's law, what does this law states? I'll take an illustration to explain what is this Kohlrausch's law. So Kohlrausch's law mainly deals with the limiting molar conductivity of both the strong electrolyte as well as your weak electrolyte. More importantly, it deals with calculating the limiting molar conductivity of a weak electrolyte with the help of a strong electrolyte. Say lambda m naught or m infinity of an electrolyte according to Kohlrausch's law, it is equal to lambda m naught of cation plus lambda m naught of anion. That is, it is the sum of the limiting ionic conductivity of cations, or you can also call it as limiting molar conductivity of cation and limiting molar conductivity of your anion. It is the sum of both the cations and anions limiting molar conductivity. So that's your sum up with your electrolytic molar conductivity. Ionic conductivity, you call it as limiting ionic conductivity. That is nothing but it is the limiting molar conductivity of an ion. It is either a cation or an anion. It is just called as your limiting ionic conductivity. Say for example, I take an example of say lambda m naught of NaCl. I can write it as lambda m naught of Na plus lambda m naught of Cl minus. So this is an example of a strong electrolyte, that is NaCl. It is a limiting ionic conductivity of sodium ions plus limiting ionic conductivity of your chloride ions. I'll take another example of say lambda m naught of MgCl2, magnesium chloride. So it will be lambda m naught of Mg2 plus lambda m naught of Cl minus. Since there are two Cl minus ions, I have to multiply this by 2. Summarizing from example 1 of your NaCl and your example 2 magnesium chloride, now I can describe what is this Kohlrausch's law. What is this Kohlrausch's law? Very simple. It describes as the limiting molar conductivity of an electrolytic solution or electrolytic substance is the sum of the limiting ionic conductivities of each ions, each cation and anion, multiplied by their respective numbers in the balanced formula. So here I have balanced it, that is it is 2 ions, so I have to multiply it by 2. So that is called as your Kohlrausch's law. So let us see the statement. The limiting molar conductivity of an electrolyte, the limiting molar conductivity of an electrolyte, that is lambda m naught, is the sum of limiting ionic conductivities of cation and anions multiplied by their respective numbers present in one formula unit. That is the limiting molar conductivity of an electrolyte is the sum of, very important, it is a sum of limiting ionic conductivities, that is lambda m naught of cation and anions multiplied by their respective numbers present in one formula unit. I can describe this one formula unit in terms of your NaCl, wherein Na is also 1 and Cl is also 1. One formula unit of magnesium chloride, 1 unit is of your magnesium while 2 units of your chlorine. So as a result, in one formula unit, how many ions are present, you have to multiply by that. So this is about your Kohlrausch's law. So as already I have told you, the main application of Kohlrausch's law is, since you cannot determine the limiting molar conductivity of a weak electrolyte through your graphical representation, Kohlrausch's law helps in calculating it through the this formula, that is this your Kohlrausch's law formula for your weak electrolytes using your strong electrolyte. So I will be taking two illustrations of two weak electrolytes. One will be your acetic acid as well as the other one is your ammonium hydroxide, and we will be deducing how to calculate the molar conductivity, limiting molar conductivities of these two electrolytes using strong electrolytes limiting molar conductivity. As you all know, the limiting molar conductivity of strong electrolytes can be determined through your graphical representation. As it coincides with your y-axis, you can determine it through your graphical representation. So let us see that. So application of Kohlrausch's law, that is calculating the limiting molar conductivity of a weak electrolyte. Here I have taken the weak electrolyte acetic acid using three strong electrolytes, that is your NaCl, HCl as well as sodium acetate. It's a salt of sodium salt of acetic acid, so it's also a strong electrolyte. So using these three electrolytes values, I have to now deduce the value of this acetic acid's limiting molar conductivity. So first let us see what you have to calculate. Very simple, you have to calculate lambda m naught of acetic acid, that is I can write this as lambda m naught of CH3COO minus plus lambda m naught of H plus. Say this is your first equation. So acetic acid has a cation and an anion. Anion is your acetate ion and H plus is your cation. So it's the sum of both the things. Since there are only each ions one in each, so only 1 multiplied by 1. So this is the equation I wanted finally. The other three are NaCl, HCl and acetic acid. So NaCl, lambda m naught of NaCl, I can write this as lambda m naught of Na plus lambda m naught of Cl minus. The value is given, it is 126.4 Simon centimeter square per mole. Simon centimeter square per mole. So this is equation 2. Equation 2. Then lambda m naught of HCl, it is equal to lambda m naught of H plus lambda m naught of Cl minus is equal to, the value is given, it is 425.9 Simon centimeter square per mole. So this is equation 3. The last strong electrolyte is sodium acetate, that is lambda m naught of CH3COO Na is equal to lambda m naught of say Na plus lambda m naught of CH3COO minus. That is equal to, the value is given to be 91.0. So 91.0 Simon centimeter square per mole. Now the agenda is, using these equations 2, 3 and 4, you have to deduce equation number 1. That is, using equation 2, 3, 4, either you sum up or you subtract these equations. The final equation should be your equation 1. This is just like your Hess law that you have studied in your thermodynamics. So in Hess law also we will be having 4 different equations, one deduced equation. So those 4 equations you have to multiply it, or you have to sum it up, or you have to subtract it. Finally you have to get the equation. Same like your Hess law. Using these 3 equations, finally I have to get this equation. So this is the equation I want. So this is the equation I want. You have to use these equations. Either you have 2 options, you sum it up, or you have to subtract it. Finally you have to get this equation. So for the first equation, you can see that the one of the ion I require is your acetate ion. So acetate ion is present in which equation? In the fourth equation you have acetate ion. So fourth equation I will be taking first. Acetate ion is present, along with that sodium ion is present. We do not require sodium ion, only we want your acetate ion. So first I will write equation 4. So in equation 4 I want only acetate ion. What should I do for the sodium ion? Sodium ion should be operated in such a way that this has to be deleted. So I have to look into sodium ion, in which equation it is present. 2 and 3 are there. You can observe it is present in equation 2. So equation 2, equation 4, there are sodium ions, they have to get cancelled out each. As a result I have to do, sodium ion is here, so minus of this equation 2. So minus equation 2. So now what happens? The sodium ions get cancelled, but in equation 2 there is Cl minus ion remaining. In my required equation 1 there is no Cl minus ion. As a result, equation 2 Cl minus ions also should be minused. So what I have to do? Where is Cl minus ion present? The Cl minus ion is present in third equation. So third equation, this is already minus, so this has to be plus, so that they get cancelled out. So plus equation 3. So I will deduce what does this look like. That is lambda m naught of Na plus lambda m naught of CH3COO minus, this is your equation 4, minus equation 2, this is your lambda m naught of Na plus lambda m naught of Cl minus, plus lambda m naught of H plus lambda m naught of Cl minus. Now the equation becomes, you can observe lambda m naught of Na plus remains as it is, plus lambda m naught of CH3COO minus, plus into minus, so minus lambda m naught of Na plus into minus lambda m naught of Cl minus, plus lambda m naught of H plus lambda m naught of Cl minus. So Na plus they get cancelled out. Acetate ions limiting molar conductivity remains as it is. Cl minus plus Cl minus they get cancelled out. Finally the remaining thing is your lambda m naught of H plus and lambda m naught of your acetate ion. That is your required equation. So the equation that is substituting the values here, accordingly we have got this one, that is lambda m naught of CH3COO minus plus lambda m naught of H plus, that's nothing but I can write this as lambda m naught of CH3COOH. So this was the equation that was required, which I have got by operating the equations like this. What is the operation? Equation 4 minus equation 2, equation plus equation 3. I have got the equation. So now what I have to do? For these equations, what I have operated, I have to substitute the values. So equation 4 value minus equation 2 value plus equation 3 value. So let us see what is the substitution. So equation 4's value is 91.0. So 91.0 minus equation 2 is 126.4 plus equation 3 is 425.9 Simon centimeter square per mole. This will be equal to Simon centimeter square per mole. So it will be 390.5 Simon centimeter square per mole. This will be the lambda m naught of acetic acid. So like this, you can calculate the limiting molar conductivity of a weak electrolyte using strong electrolytes. Next illustration will be another weak electrolyte, that will be your ammonium hydroxide. So the next thing is, you have to calculate the lambda m naught limiting molar conductivity of an ammonium hydroxide. If lambda m naught of barium hydroxide, ammonium chloride as well as your barium chloride is given as it is. The same method, but the problem is different, that's it. So ammonium hydroxide, lambda m naught of ammonium hydroxide is equal to lambda m naught of NH4 plus lambda m naught of OH minus. This is your equation 1 and this is the equation required. Using these three electrolytes, you have to deduce this equation. The second equation goes to be your barium hydroxide, lambda m naught of barium hydroxide, it's equal to lambda m naught of barium 2 plus 2 hydroxide ions are present, so 2 into lambda m naught of OH minus, this is equation 2. Lambda m naught of ammonium chloride NH4Cl is equal to lambda m naught of NH4 plus lambda m naught of Cl minus. This is third equation. Finally, a fourth one, it is your barium chloride. Lambda m naught of barium chloride, it is equal to lambda m naught of barium 2 plus lambda m naught of Cl minus, equation 4. The values goes to be like this. This is your barium hydroxide, 500 Simon centimeter square per mole, and ammonium chloride is 120 Simon centimeter square per mole, and finally your barium chloride, it is 300 Simon centimeter square per mole. Again, using equation 2, 3, 4, you have to do such operations that you get this equation number 1. Either you can have a addition or a subtraction. Using these 3 equations, you have to get this first equation. That's the agenda of this problem. So in this first equation, required equation, you can observe that ammonium is required. So you can observe, where is ammonium ion here? Equation 2 has an ammonium ion. So first equation is your equation 3, ammonium ion is present. So ammonium ions are present in your required equation, so that is present in equation 3. So it is equation 3. But in equation 3 you can observe Cl minus ions are present, which is not required, so I have to cancel it out in such a way that in another equation they have to get cancelled. So which is the other equation has Cl minus ions? It's your fourth equation where you have Cl minus ions. So it has to get cancelled out, so it is minus equation 4. In equation 4, equation 3 Cl minus ions get cancelled with equation 4 Cl minus ion, but barium ions will be remaining. So barium ions has to be cancelled out. Which is the thing where present in which you have your barium ions is, it is present in your this one, that is your equation 2. So this has to get cancelled with this one. Since this is minus, obviously this has to become plus. So plus equation 2. So what happens to the equation if I write it out? Equation 3 is lambda m naught of NH4 plus lambda m naught of Cl minus of, so minus of equation 4 is this one, that is lambda m naught of Ba2 plus lambda m naught of Cl minus. Sorry, here you have to multiply it by 2 because BaCl2 is twice, so 2 into lambda m naught of Cl minus. 2 into lambda m naught of Cl minus. Then is equation 2. So equation 2 plus equation 2 is lambda m naught of Ba2 plus lambda m naught of 2 into lambda m naught of OH minus. So if I deduce this equation, you can observe that there is 1 mole, that is 1 ammonium ion, lambda m naught of 1 ammonium ion, lambda m naught of 1 Cl minus ion. But you can observe here it is 2 into lambda m naught of Cl minus ion. So in the required equation, I don't want the Cl, so I have to cancel it out. But here it is 2, but here it is 1. So what should I do? This equation 3 into 2 I have to do, that is 2 into equation 1. So 2 Cl minus ions, 2 Cl minus ions, they get cancelled out. So then equation becomes 2 lambda m naught of NH4 plus 2 lambda m naught of Cl minus lambda m naught of Ba2 minus into plus minus 2 lambda m naught of Cl minus plus lambda m naught of Ba2 plus 2 into lambda m naught of OH minus. So 2 Cl minus, 2 Cl minus ions, they get cancelled out. Barium, they get cancelled out. The remaining equation will be 2 lambda m naught NH4 plus 2 lambda m naught OH minus. The required thing is 1 each, but you have got 2 each in each. What should you do? Divide it by 2. What the value you get? Divide it by 2. So the equation have got, I have to substitute the values now. So I have got this one. So that is divided by 2. If I make divided by 2, the equation becomes lambda, that is lambda m naught of NH4 plus lambda m naught of OH minus. So this is the equation required for you. So what do you get the answer? Divided by 2. So let us see what you have to do here. So 2 into equation 3 value is 120 Siemens centimeter square per mole. So 2 into 120 minus equation 4 is 300 plus equation 2 is 500. And I have told you it is whole divided by 2. So the value becomes, it is equal to, the value becomes 220 Siemens centimeter square per mole. So this is your limiting molar conductivity of your ammonium hydroxide that has been deduced using 3 strong electrolytes. One is your barium hydroxide, barium chloride, as well as your ammonium chloride.